Hello, and welcome to the Applied AI News. This is a special issue on learning to think. Today, we're diving deep into the fascinating world of aligning large language models to think and reason, specifically focusing on DeepSeek's R1-Zero. We'll explore how this model pushes the boundaries of LLM reasoning and what makes its training process so unique. Before we get to R1-Zero, let's quickly recap the typical landscape of LLM fine-tuning. We usually start with a pre-trained LLM, and then we refine it for specific tasks. One way to do this is through supervised fine-tuning, or SFT, where we provide the model with countless examples of query response pairs. The goal here is to directly modify the model's parameters so it learns to generate the correct answers from a given input query. This is essentially teaching the model a direct mapping from inputs to outputs based on the examples we give it. Fine-tuning is just the first step. To further refine the model's functional behavior and make sure its responses are not just correct but also helpful, we need to align it with our preferences, a process called language model alignment. This is where reinforcement learning comes into play. We often use algorithms like proximal policy optimization, or PPO, which is part of the broader family of policy gradient reinforcement learning algorithms. Policy gradient methods optimize a policy, which in our case is the LLM, to make better decisions based on the rewards it receives from the environment. The policy is essentially the strategy that the model uses to choose an action given a certain input, known as state. Now, this is where things get a bit more complex. PPO aims to shape the LLM's behavior by providing it with reward signals based on how aligned it is with some given preferences. But here's the catch: figuring out how to reward an LLM effectively. Historically, we try to do that by collecting large datasets of human-preferred responses to different queries. Then the challenge was to build a very good preference model that could accurately capture human preferences. The preference model would score every generated output of the LLM, and that score would feed the optimization objective. Intuitively, the preference model should be able to distinguish between a text that would be preferred by a human and the one that would not be preferred by a human. If we were to use PPO, it would require us to create a very good, accurate human preference model. It needs to be a good and accurate model of human behavior to generate a score that guides our LLM to output better responses. It's important to remember that reinforcement learning methods like PPO and its variants work by optimizing the model's existing capabilities, not by building new ones from nothing. If a model has no understanding of a domain, reinforcement learning won't magically make it better. It just fine-tunes behaviors that are already present. Think of it like a coach helping an athlete refine existing skills, rather than magically giving them new ones. That's why pre-training still matters. The model needs to start with a good foundation of knowledge. Reinforcement learning then helps refine how it applies that knowledge. Once we have a fine-tuned and aligned language model, we can then prompt it where we tell the model how to do things, and sometimes even how to think. Methods such as chain of thought and tree of thoughts are examples of enforcing a specific reasoning structure on the model to enable correct answers. These techniques essentially guide the model to break down complex problems into smaller, manageable steps. For example, chain of thought prompts the model to explicitly show the steps it takes to arrive at the final answer. Tree of thoughts pushes this further by exploring multiple lines of reasoning before settling on the most promising path. These prompts give the model a predefined strategy for approaching problem solving. So, with all that said, what makes DeepSeek's R1-Zero so special? We've been talking about training LLMs to match human or model-based preferences, but R1-Zero adds a new layer. Instead of just focusing on the final answer, R1-Zero trains the model to produce reasoning paths along with that answer. This removes the need to explicitly prompting the model on how to think to arrive to an answer. Rather, the most effective reasoning strategy emerges during the alignment step. During R1-Zero's alignment, the model is asked to generate two things for each query: the thoughts and the final answer. Now, this is crucial. While we obviously want the answer to be correct and match the ground truth answer in our dataset, we also want the model's thoughts to logically lead to that correct answer. The core idea is that if the answer is correct, there's a strong chance the reasoning process or the thoughts that the model went through is also effective. It is very similar to what a human would do when solving a complex problem. First think and rationalize, and then give the answer. However, unlike explicit prompting methods, the thinking strategy is not encoded in the algorithm or in a prompt. It emerges during the training process. While the model is trying to arrive at the correct answer, it implicitly revises its reasoning paths in the process to create the most effective one. The reinforcement only provides feedback on the answer, but the reasoning is implicitly needed to be correct to arrive at the correct answer. This leads to emergent reasoning. To perform the alignment, DeepSeek R1-Zero uses a modified version of PPO, which we discussed earlier, called Group Relative Policy Optimization, GRPO. The GRPO algorithm is based on optimizing an objective to maximize how often the model generates better responses. Think of it as a continuous learning process. Model tries, sees how good it was, and then tries to do better next time, while not forgetting what it knew before. The focus is not just about getting better at giving the right answer, but also doing it in a better way. In essence, we're optimizing the model's policy, which we call pi_theta of O given Q. Remember, a policy is simply an algorithm that receives a question Q and generates an output O. In the R1-Zero case, O is the model's output containing both the thoughts and the answer. Our optimization objective wants two things. 1. Improvement based on PPO. We want pi_theta of O given Q to improve compared to the previous version of the model, like in PPO. Essentially, if a generated thought process leads to the right answer, we want the model to generate more like that in the future. 2. Stability based on KL divergence. We don't want the model to change too drastically from the previous version, so we include a KL divergence term to ensure the model doesn't suddenly forget what it already knows. A core part of the algorithm is calculating the reward and advantage, which is a measure of how well is the model doing. To do this, R1-Zero uses a simple accuracy reward system. It is rule-based, checking the output of the LLM against the known correct answers. For instance, with math problems, it verifies the final answer's correctness based on predetermined formats. For programming problems, it uses a compiler and test cases for evaluation. There is another reward called format reward, and it ensures that the model puts the thoughts between those think tags. This advantage score guides the optimization process. If a model produces a correct answer with a relevant thought process, it gets rewarded and nudged to continue behaving that way. This isn't about explicitly teaching the model how to think in a prescribed manner, but rather setting up an environment where the most effective and correct thinking patterns are implicitly rewarded and thus naturally emerge. One key piece in the R1-Zero training is the grouped nature of the optimization. Since LLMs are stochastic and can give varying results, relying on a single output for evaluation can be unreliable. Grouped direct preference optimization solves this by generating a set of outputs for the same query. It evaluates the overall quality of this group of answers, giving a more stable and consistent advantage signal, instead of relying on a single potentially random result. It also makes the model more reliable and better at generating consistent outputs. Think of it as getting multiple opinions instead of just one, and using the average quality of those opinions to guide the training. In practice, the DeepSeek needed to first fine-tune the base model so that the model behavior is close enough to the desired outcome with specific formatting. The model was then aligned by the GRPO instant of reinforcement learning and finally fine-tuned again for optimal outcome. So, what's the big deal with training a model to generate its reasoning? By optimizing not just the answer, but also the thought process that leads to the answer, R1-Zero isn't simply memorizing correct responses. It's forced to invent and learn effective reasoning strategies, like the famous aha moments, step-by-step chain-of-thought reasoning, and many other problem-solving approaches. It is not just optimizing to output the right answer, but also to achieve it in a way that is robust and generalizable, leading to emergent reasoning capabilities. R1-Zero basically discovered the best way to think in the domain it was trained on to achieve the desired results. And here's an important point that highlights the sophistication of our R1-Zero. Reinforcement learning techniques, like the one used here, are most effective when the model already has a basic understanding of the task it is being asked to do. In this case, the pre-trained LLM already has a basic ability to generate text. RL is not optimizing the base text generation capabilities. Instead, RL optimizes how that base text generation behavior is used to solve complex tasks. So, RL guides the model to use the text generation ability for problem solving at a higher level. It fine-tunes the model's behavior rather than its basic functionality. In essence, DeepSeek R1-Zero pushes LLM alignment beyond just matching surface preferences. It's about teaching the model to think, to reason its way to the right answer. This approach opens doors to more robust, reliable, and explainable AI models. Thanks for watching. We'll be exploring more advanced AI techniques in our next video. Don't forget to like and subscribe for more content.